Hello, everyone. So today we're going to run through our Chem 1 notes from Unit 6 on percent yields. So a percent yield is the amount of a product actually produced from a reaction compared to the amount of product you would expect to get if everything worked 100% perfectly. Um, I don't I don't know if you've ever heard the term yield before. Like farmers use it a lot of times. Like they'll talk about crop yields, which is the amount of crop that they pull out of the field that they get that grows. Uh, so the idea here in chemistry is, and we talked about this. We've talked about this with the stoichiometry stuff we've been doing, and with those limiting reactants and things. Is that um, based on the math, based on the reaction, the balanced equation and such, we should be able to figure out different amounts of things, the amounts of reactants we need, the amounts of products we make, stuff like that, right? But those numbers from those problems are all based on uh, everything working 100% perfectly, really, based on the equation and everything like that. And again, in real life, we know that it's very rare that things go 100% perfectly, right? We, maybe some of the reactants get lost or don't get transferred fully. You can, in a reaction, you can have other unintended side reactions occur with other, whether it's gases in the air, other things that it comes into contact with, where it doesn't, give you um, a full reaction or whatever. So that's where percent yield comes in. It helps you understand like how much in real life was actually produced compared to the amount that mathematically you figured out should be produced. All right. So the equation, like we have here, is percent yield equals what's called the actual or measured mass. Okay, so this is what you would actually measure in a lab. Okay, now for us with homework, this will be given to you. The actual amount will be given to you. It'll say in the problem, something like so much of thing is produced. So, like for example, in number one here, what is the percent yield of water if 25.6 grams of CH4 is combusted according to the following reaction, and 45.0 grams of water is produced? The 45.0 grams of water is the actual amount of water that was produced, like if you're doing it in a lab or whatever. Okay. The theoretical or calculated mass is what it says here, the calculated, or what you get from doing the math. It's the amount that should be produced if everything worked 100% perfectly. All right. So let's take a look at a problem here. So the one I just read, we've got the balanced equation they give us. Now, we have, and I'm going to highlight here. So there are two things that we will typically be given in these type of problems. All right. One is amount of reactant or reactants. Two is the actual mass of a product. Okay, so we want to identify, like where these things are, what these things are. So I'm going to highlight here the amount of reactants and the actual mass of the product, which is the part that goes up here as well. Okay, so if we look at our problem here, what is the percent yield of water if 25.6 grams of CH4 is combusted according to the following reaction and 45 grams of water is produced? So I already told you, like, the 45 grams of water is the actual. How do we know that? Well, if we look at the things that we're given here, 25.6 grams of CH4, that's CH4 is over here on the left side. That means it has to be a reactant. 45.0 grams of water is over here, meaning it's a product. This is the only thing that they're giving us an amount of a product, which means it has to be the actual mass. The actual mass is the actual mass of a product. That has to be on the right side of the equation. The substance does. Okay, which means they're going to give you either one amount of reactant or more. So here, they're just giving us one reactant. So this example only has one reactant. And when I say one reactant, I don't mean there's only one reactant. I mean only has, it should be only gives the mass of one reactant. Okay, which means that reactant is automatically the limiting reactant. In other words, they told us we have this much CH4. We're going to assume that amount of CH4 is the thing we're going to run out of. That's because we're going to assume we have more than enough of the other reactants. So we can convert directly into the desired product. We don't have to do the BCA chart because we know the one that runs out first. We know what we are using to find all the other stuff. So we need to do this. We need to find the theoretical mass. The theoretical mass is just the amount of product that we should get if everything works 100% right according to the math. So this is just the stoichiometry stuff we did about a week ago. You're going to start with the reactant that you were given. So we're starting with the 25.6 grams of CH4. Okay. And we are going to turn this into the desired product. The desired product, we want to get the theoretical mass. How do you know which thing you're going to? We've got CO2 and H2O. Which product? Well, it's the water, because we want to know the percent yield of water. All right. And if they just say, what is the percent yield? They don't say of what? Then look at the actual they gave you. Whatever substance the actual is for, that's the percent yield you're looking for. Okay. All right. So we need to get this into grams of water. So we're going to go grams of CH4 to moles of CH4. Okay, and this is following that flow chart. Hold on one second. Let's see. Okay, so doing this is just, following this flow chart. We're here, mass of our beginning substance. We need to turn into mass of a new substance. So we're mass of our beginning substance into moles of that, then moles of our beginning substance into moles of our new substance, moles of our new substance into grams. That's what we need to do. So grams of CH4 into moles, it's 1 mole. The molar mass, carbon is 12, hydrogen is 1 times 4, so that would be 16. Then we're going to go moles of CH4 into, we're trying to get into water, so moles of H2O. Remember, mole to mole, this is the only time you use the coefficients from the balanced equation. So our balanced equation is here. So in front of H2O, there's a 2. In front of CH4, there's nothing, so it's a 1. Then we go moles of H2O on the bottom, because it's up here. Turning it into grams of H2O. Moles to grams is 1 in front of the mole. Grams of water is 18. And we just do the math. Okay, so this is, let's see. So this comes out to be 57.6 grams of water. Okay, this is the amount of water. This is the amount of water that would be made if we used all of the grams of CH4, if everything worked 100% perfectly. Okay, so this is our theoretical. So to get the percent yield, okay, all we need to do is take the actual that we were given. So we're doing actual over theoretical times 100, right? So our actual, 45, over our theoretical, 57.6, times 100. This is our percent yield. So we get 78, 3 significant figures from our numbers from the problem. So 78.1%. And that's the label is just percent. It's a percent yield. So what this is telling us is that if this was done like in an actual lab or whatever, and they got 45 grams of water, that would be 78% of what they should have gotten if everything worked 100% perfectly. Okay? All right, let's take a look at the second example here. Now, what is the percent yield in a reaction between 53.8 grams of aluminum chloride and 73.5 grams of iron 2 sulfate if 51.6 grams of aluminum sulfate is recovered? So let's look at this again. Remember, they have to give us the actual. So let's find the actual first. We should identify that. The way we're going to know is it will be the only thing they give us the amount of that's on the right side of the equation. So if we look, aluminum chloride, that's aluminum and chlorine, so that would be this one. That's on the left side. Iron 2 sulfate, iron is Fe, sulfate is the SO4, so that's over here. That's on the reactant side, that's not it. So that means this 51.6 grams of aluminum and sulfate right here. That's a product, it's on the right side, which means this is our actual. So we don't use that until the end where we do the percent yield. Okay, which means, as we already looked, these other two things are our reactants. Okay, now I'm going to show you 2 ways to go about solving this when you've got 2 or more reactants. You can choose whichever way you like better. If the first way, I'm going to try to do it what I think is the, I won't say easier. I think it's easier because we've already been doing the BCA charts. I'm going to do it that way first. And if you understand that and you just want to do that, you can just literally like stop the you can stop the video there and you don't have to watch the second way. If you want to watch the second way to see it because the second way might be a little faster, you can try that. It's totally up to you. All right. So the first way is doing essentially a BCA chart idea and find limiting reactant stuff. So let's find the limiting reactant first. The way we find the limiting reactant, remember, is we have to turn. So we have, let's see. Okay. So B, C, A. Okay. So remember, whole BCA charts in moles, right? So the first thing we need to do, given us these in grams, we have to turn the grams into moles. So I'm going to 53.8, and sorry, let me move this up a little bit here. I'm going to start it kind of over on the left side here, so I make sure I have enough room. So grams of the aluminum chloride, so that's the AlCl3. And I'm going to convert grams of AlCl3 into moles AlCl3. So 1 mole aluminum chloride is, let's see, 1 times, what's aluminum? 27 plus 3 times chlorine is 35.5, gives us 133.5. All right. So we take 53.8 divided by that, and we get 0.403. I'm going to go to at least as many significant figures as we have here. So 403, you can keep going. You can take it out longer if you want. Just don't make it a lot shorter because it can mess your numbers up. Moles of the AlCl3, right? So that's going to go up here. Remember, that's the number before. So that's the number of moles, 0.403. Okay, we're going to do the same thing with the iron 2 sulfate. So 73.5 grams of the FeSO4. And we're going to go grams of the FeSO4 to moles. Okay, iron is 55.8 times 1 plus sulfur is 32.1 times 1 plus 4 times 16 for the oxygen gives us 151.9. Okay, so we do 73.5 divided by 151.9 gives me 0.484 moles of the FeSO4. Okay, that goes here. Now, to find the limiting reactant, remember, you're not comparing these. There's one step you have to do before you can compare to find the limiting reactant after you get the moles. These are zeros, right, for the products. Okay. We need to divide by the coefficients before we can determine the limiting reactant. So in front of AlCl3, there's a 2. And in front of FeSO4, there's a 3. So all right. So this tells us right here that our limiting reactant is the FeSO4. Okay. All right. So why did we do this? Well, because we're doing parts of the BCA chart, right? Now, why do we, okay, I guess I should back up for a second. So we need we need the limiting reactant, but why do we need that? We need that because we're trying to find the amount of a product that would be made if everything works 100% perfectly. We didn't need it in our first problem because we already know what the limiting reactant is, so we use that to convert. Down here, we didn't know what the limiting reactant is, so we need to find that one. So because we need to know basically which one of these runs out, which one of these is going to determine the amount of aluminum sulfate that should be made. Okay. Now, if we look at this, we need to do the percent yield problem. We need to find the theoretical. We need to find the theoretical mass. The mass of the aluminum sulfate that should be made if everything works 100% perfectly, right? So if we're looking, I guess I am going to highlight. So theoretical. So in the first problem, this was our theoretical right here. Okay. And our second problem here, we need to find the amount of aluminum sulfate that should be made if everything works perfectly. On our BCA chart, where is that going to be found? Well, aluminum sulfate's here. The amount that we have after the reaction is done is going to be here. But you have to remember that that's going to be in moles, right? So here's the thing about doing this. We only need the grams of the aluminum sulfate. We don't need any of this other information for this problem specifically, because all it's asking is percent yield. Now, if it was asking for other stuff like how much excess reactant, then we would need to do the rest of the chart. But for this problem, we only really need to do this part of the chart. Okay, so knowing what the limiting reactant is, to do the change row, remember it's the coefficient times the limiting reactant smaller number. But we only need this column. So I'm going to take smaller number here times the coefficient in front of aluminum sulfate, which is a 1. So this is just going to be 0.1613. To get the after part, it's a product, so we add. Remember, subtract reactants, add products. So we add, so we get 0.1613. This is in moles. We need grams, right? So we're going to take 0.1613 moles of aluminum sulfate. We are going to turn that into grams. Now, this one's got some pretty big math, or you got to kind of watch your stuff on this when you're doing the mass of it. So the 2 just goes to the aluminum. So aluminum is 27. So 27 times 2 plus. Now the 3 goes to everything in the parentheses. It doesn't affect the 2 with the aluminum. It just affects everything in the parentheses. So we got 3 sulfurs. So we got 3 times sulfur is 32.1 plus, it goes 3 times 4, we've got 12 oxygen. So 12 times 16. Add it all up, we get 342.3 for the grams of aluminum sulfate. So we do the math on this. And we get 55, significant figures are 3, so it'd be 55.2 grams of aluminum sulfate. Right? Now, what is this? Well, this is it's our theoretical. It's the amount that we should make if everything works 100% perfectly, the amount of aluminum sulfate. Okay, so to do the percent yield, we're taking, remember, again, actual over theoretical times 100, right? So we've got our actual, remember the actual marked here, theoretical. So we've got the actual from up here, so it's the 51.6 over the theoretical that we figured out, 55.2 times 100 gives us a percent yield of 93.5%. That's our answer. Okay. So that's one way to do this. Okay. If that way makes sense and you like it because it's using the BCA chart, and that's what we've been doing, then you can just stop right now and you're good with the video. If you want to see the second way, which might be a little shorter work-wise, but it's kind of learning a new way to think about it, or kind of applying stuff in a different way, then hang with me here. Okay. All right. So second way. The second way is similar, except we're not gonna kind of like do the BCA chart diagram thing. So we still have to find the limiting reactant. Okay, that is an absolute must. We have to know that. So I'm gonna copy down the stuff that I had from my limiting reactant from before here. Let me angle this a little bit so I can. Okay, so I'm going to copy down. So I'm going to just go through. You'd go through the step to find the limiting reactant. So we would do. So this would be kind of like method 2, I guess. So I'm going to have 53.8 grams of the AlCl3. I don't need to talk through all this. You guys heard it with the first one. You could probably just fast forward till I get this written if you wanted. Okay, so now that I've gotten this, and we've determined, right, that our limiting reactant is the FeSO4, correct? All right, so if we look at this, okay, now I'm gonna do something in a different color here, blue, to explain something, and then I'm going to go back and show you how we would apply it. Okay, so if we look, so FeSO4 is our limiting reactant, so that's going to determine the amount of product that's made, right? So I'm going to take this, so 0.484 moles of the FeSO4, right? And I'm going to turn that into the grams of aluminum sulfate. Okay, so I'm going to go moles FeSO4 to moles of the aluminum sulfate, the Al2SO43. Okay, so in front of the FeSO4, these are coefficients, right? So it's a 3. In front of the moles of Al2SO43, it's a 1. And then I'm going to go into, from moles of Al2SO43 into grams Okay, so 1 mole and for, what did we say the grams were before? We already did the math. 342.3. So 342.3. Okay. And watch what happens when we do the math on this. 0.44 divided by 3 times, we get 55.2. Which was our theoretical, right? Okay. Now, the blue is not the work you would actually do and show. I'm showing you that so you understand what I'm going to do next. Okay. Look at where we're at. So we've identified FeSO4 as our limiting reactant, correct? All right. At this point here, right here, compare so I started with the 0.484 right here, right? What did we do to get to this? Well, we did the molar ratio conversion, right? And then times the grams. So, but when you find the limiting reactant, you've already done this part of this conversion here. You have already done the dividing by the coefficient for the limiting reactant. So, what part do we need to do to get to what we want to be in? Well, we got to do the rest of this, right? So, once you get this number after the number that helped you figure out the limiting reactant, what you are going to do is you're going to take that number times the coefficient for the theoretical. So like what we're trying to put it into. So you take it times the coefficient of the theoretical, and then times the molar mass. Okay, we would do this part of it right here. Times that, and then this is always going to be 1 at the bottom, so times that. So we would take this times the coefficient for the theoretical. The theoretical is Al2SO43. The coefficient is a 1 times the molar mass for that. for the theoretical. 342.3 grams, and we're going to get that number. This number is our, gotta make sure you use the red highlighter here. This number is our theoretical amount. Now all we would need to do, okay, remember the blue was just kind of explaining why we do this. So underneath here, I'm going to put like the next step we'd actually do, which is we would take the actual from the problem. We would do this. We take the actual from the problem. So we take the percent yield equals the actual 51.6 over the theoretical 55.2 times 100. Sorry, I didn't realize I wasn't on the screen there. So this is the actual. This is the theoretical times 100, and it's going to give us the same. Okay, so again, remembering the blue you wouldn't be doing and showing, but this would be the work. You'd find the limiting reactant, and then you'd take the limiting reactant one times the coefficient for the theoretical times the molar mass. That gives you the theoretical grams, and then you just do this down here. So if you like that way better than the BCA chart, partial BCA chart one, go ahead and use this. Either way you go, you still have to show the work that I told you need to show. All right. If you guys have questions, let me know. We're actually going to work on the homework in class when you guys come back. So it's just the lecture for now.